Today we are going to continue our discussion of the chapter 10, the properties of the wave. So what we have studied before is that we define the quantities, the amplitude, wavelength, the frequency, and the period to describe the motion of the wave. And we also introduced you that all the waves can be categorized into two types of wave. One is the transverse and the second one is the longitudinal. And then I give you several examples of the wave. Today we are going to study is that when the wave propagate in the space, when they interact with the surface, when they interact with the second wave, what will happen? But let's try to refresh the basic quantity you already learned before. So this is for the concept of the transverse wave. So what do I mean by the transverse wave? You can see the mediums of the wave is oscillate up and down, but the wave is propagating to the right. So the direction of oscillation of the median is perpendicular to the wave propagation itself. So there are two different kind of concept of direction when we study the wave. The movement of the particles and the movement of the wave, they are totally different concept. And when we're talking about the wave, they only carry the energy away from that. They don't take the particles with them. Also, when you try to describe the wave, you need to know that what is the wavelength. So for example, the wavelength could be the distance traveled by the wave within two adjacent crests or throats. And the amplitude is that the biggest vibration of the median can vibrate. And when we define the period, what do we mean by the period? It is the time spent for the wave to propagate for one wavelength. And finally, what is the frequency? Frequency is that how many cycles can be completed by the wave within 1 second. So this is a figure better summarize almost all the fundamental quantity we have studied before. So therefore, the wave is described by the frequency, the amplitude and wavelength, and also the speed. How fast does the wave propagate? But how do we calculate the wave speed? It is equivalent to the multiplication of the frequency multiplied by the wavelength. So let's try to use the knowledge we learned from the chapter 1. The velocity is the distance divided by the time. So the distance traveled by one wavelength is lambda, and the time spent is one period. So this is how you calculate the wave speed. But because we know that 1/t is the frequency f, so therefore this is the most common formula you're going to see, is that the wave speed is actually the wavelength multiplied by the frequency. Now let me use the longitudinal wave as an example to you. Then how does the wave propagate? So if you have an instrument, they vibrate. The vibration of the instrument also will bring the air particles near that start to vibrate. And what will happen is that now you will see the air particles will become compressed and rarefied. So in some regions you have more air particles, some area you have much fewer. So this kind of vibration is actually passed through the media. So media also start to vibrate. But you can see that the media is oscillate back and forth in the direction of the wave propagation. And this is how we define that this kind of wave is the so-called longitudinal wave. But still, the propagation of wave is simply just due to the vibration of the medium. And the sound wave is a very typical example for the longitudinal wave. And last time I also introduced you another example for the wave, which is water wave. So water wave is not a pure longitudinal wave or transverse wave. It is a combination of two. So you throw a stone into the pond and they will produce a spherical wave outward. So you may say, okay, now it looks like it is a transverse wave. But if you look at the structure of the surface of the water, you will find that this is the case. So the water wave, when they're passing through, they will bring the particles originally a little bit to the right and the downward and a little bit to the left and upward. So actually, it is a combination of two. Okay. So now let's have the first conceptual quiz today. So if you dip your finger repeatedly onto the surface of the still water, so actually you are producing the wave, and also you periodically produce the vibrations. So now if you dip your finger more frequently, what will happen? So the answer is that the frequency you produce is actually the frequency of the wave produced. Apparently, so now the more frequently you dip, the higher the frequency of the water wave will propagate. And the higher frequency means the shorter wavelengths. So in the last lectures, we also studied the reflections. So now when the wave propagates in the space, there's no way they can propagate smoothly without interacting with anything. Yeah? So they will hit with the surface. And when they hit the surface, they will return and change the directions. But how does the direction is determined, the return direction? Then they follow the so-called laws of the reflections, which is the angle of incidence is equivalent to the angle of the reflections. So if this is the surface, no matter what kind of surface, at the point of incident, the light, this is the direction of wave propagation, they will hit on this point. Then at this point, you will draw a normal line, which is the dashed line perpendicular to the surface. And now you can define the angle, so-called the incident angle, theta I, compared with the normal line. And now the direction of the reflected light or reflected wave is this one. And the angle is theta R when they compare with the normal line. And the theta I and theta R should be the same. So this is the so-called the law of the reflections. And now, today, I'm going to focus on the second type of the interaction, which is the so-called the refraction. What is the refractions? So in the previous one, the wave propagate and hit with the surface, and they cannot penetrate through the surface. So the wave have to change the direction. Yeah. But for the refractions, when the wave propagate from one media, like the air, entering to the water. So now the surface is in between the air and water, but it is not like the surface we just have before. Now the wave actually can penetrate through into the second the medium. So now the wave can enter into the medium, but however, it is no longer the same medium. So what will happen is that the wave will be bended. So it is due to the change of the medium, and intrinsically what happens is that the speed of the wave propagating in the air and in the water is different. So that is the reason why the ray will change their directions, because they move at a different speed. So I can give you a sense of feeling what happens for the rarefaction due to the speed is different. So the concept is that the media, what I'm talking about here, the difference is due to the intrinsically, it is due to the density difference. So apparently the density of the air is much smaller than the density of water. So when the wave propagate in the space originally in the air, when they try to enter into the water, they have more particles within the water. So they meet more barrier and difficulty. So they have to move a little bit slower in order to propagate in that case. So therefore, the density of the medium is a crucial point to determine the speed of the wave. So therefore, for the sun wave, particularly now, let's try to think about that. What kind of refraction will happen when the sun wave propagate from one different media to the other one? So apparently, the speed is different. But this kind of speed difference can be understood in different kind of scenario. For example, due to the wind. Do you remember that the sun wave, the propagation is due to the vibration of the air molecules? It is oscillation, rarefications, and compression of air molecules. So uneven winds also will make the situation bigger or smaller. So uneven winds also will change the speed of wave propagation. And also, when the air is near the ground or above the ground, they also will change the velocity. So let me use the following two pictures as examples. So first, during the night, apparently everyone can experience the temperature, the surface temperature near the ground is much lower. So on the top of the atmosphere, it is warmer. So you will say, what happens? How does this affect to the propagation of the wave? So during the night, because the surface, the air is colder, so the temperature is lower, so which means the kinetic energy of the air molecules moving slower. If they are moving slower, the density is higher. So which means the lower the temperature, the higher the density, then the sound wave will propagate slower in the case. And therefore, when you are singing, so the sound wave will propagate outward. And they will find out that the sound wave doesn't propagate straightforward outward. Actually, they will be bended downward. And during the daytime, now the situation is reversed. Now the temperature of the ground surface is higher. So now the density of the ground air is smaller. So therefore, the density of the surface is smaller, so the speed is faster. So when you are singing, the sound wave will propagate outward, but now you are traveling from a high speed to a low speed. So that's the reason that it is bended. So this is the reason during the daytime it is bended upward, and during the nighttime it is bended downward. So now let's have our second conceptual quiz today. So the refraction happens when the wave travels from, the answer is D. As long as you change the density or the different kind of mediums, you better change the density. Then no matter from air to water or from the water to wave, the refractions always happens there.